All right. In this video, we're going to talk about the last theorem in this section 2.3, and that is theorem 2.3.5. That theorem says that a snark has no Hamilton cycle. So remember what a snark is. It is, first off, a three regular graph, right? That means a graph that has uh, all of the degrees. The degree of each vertex is 3, right? And so here you can see this is an example of a snark, the Peterson graph, right? You can see, verify that every snark or every vertex is of degree 3, right? So that's one of the requirements. It's a 3 regular graph. Okay, but that's not all, right? Remember that if a graph has a maximum vertex degree 3, then proper edge coloring of or the edge chromatic number of the graph, right, would have to be either 3 or 4, right, by Wiesing's theorem. So and a snark, right, is a 3 regular graph that has edge chromatic number 4. Okay, so that means that the least number of colors that you can color the edges and have a proper edge coloring is 4, not 3. Okay, so that's what a snark is. And this Peterson graph, right, is an example of one of the smaller, I guess it's probably the smallest snark. Okay, and what we want to do is prove that a snark has no Hamilton cycle. So the proof kind of goes like this. Again, we're just going to give the outline here and not the full details in this video. So but the proof would go like this. Suppose that there is a Hamilton cycle in a snark, okay? And so then we know that we can color that Hamilton cycle with 2 colors, right? And here you can see, right, they're colored red and black, this Hamilton cycle. All right, in a snark though, obviously, right, then you would have each of these, right, it's 3 regular. So each of these would have to have another edge coming off it somewhere, okay? Like so. Okay, because it's 3 regular, right? Every vertex has degree 3. So there has to be some other vertex coming off it besides the Hamilton cycle. Right? A Hamilton cycle, it goes through every vertex. So these are all the vertices, right, in the Hamilton cycle. So basically these edges, right, would have to connect from one element of the cycle to another one. And so what we're going to do is just color those a third color. So I'm going to color them blue. So for instance, all of these other ones, all of the edges in the graph that are not in the cycle are going to get colored blue. Okay, so just like I did here. Like so. Okay. And so what I claim is that that is a proper edge coloring of the snark using only 3 colors, right? So the 3 colors that we would be using are black, red, and blue. Okay. So to see that it's a proper edge coloring, what you would have to do is just go to each vertex and verify, right, that there's not 3 different colors that meet at that, are more than 2 colors, 2 edges of the same color that are incident to that vertex, right? So if you go and check, right, each vertex, so just go check any one out of here, right? We know that because that cycle is a Hamilton cycle, then that vertex is on the cycle, right? And so that means one of the edges has to be red, the other edge has to be black colored coming into it, and that leaves that third edge coming into the vertex. And since that's not in the cycle, that one has to be colored blue according to our coloring. And that's true of any vertex. So every vertex, right, has exactly one edge red incident to it, one edge black incident to it, and one edge blue incident to it. And so therefore, since every vertex has that property, we now have a proper edge coloring of the snark using only 3 colors. Okay, but that is a contradiction, right? Because by definition, a snark, right, is a 3 regular graph whose edge chromatic number is equal to 4, okay, not 3. So that would be a contradiction. And that contradicts the fact that a snark has a Hamilton cycle in it. So therefore, no snark contains a Hamilton cycle.